Look up at the night sky, and you'll see countless stars, galaxies, and cosmic wonders, but few are as hauntingly beautiful or as mystifying as the Crab Nebula. This swirling cloud of gas and dust, born from a star's violent death nearly 1,000 years ago, isn't just a spectacle of light and color. It's a cosmic enigma, a place where the laws of physics seem to twist and bend in ways that defy explanation. From its eerie pulsar heart spinning faster than a kitchen blender to the bizarre gamma-ray flares that erupt without warning, the Crab Nebula is a treasure trove of cosmic oddities waiting to be unraveled. And today, we're diving deep into its secrets, uncovering 30 of the strangest, most bewildering phenomena hidden within its shimmering tendrils. Imagine a place where magnetic fields are so intense they could rip atoms apart, where particles race through space at nearly the speed of light, and where energy surges erupt with the power of 1,000,000 suns, all within a nebula no wider than our solar system. This isn't science fiction, this is the Crab Nebula. It's been dazzling astronomers since the 11th century, when its supernova explosion lit up Earth's sky so brightly it was visible even during the day. But centuries later, we're still scratching our heads at the sheer strangeness of what's happening inside it. Why does its core flicker like a cosmic strobe light? How does it produce the most energetic radiation ever detected? And what mysterious force is behind the sudden, unpredictable bursts that leave scientists scrambling for answers? This isn't just a story about a distant cloud in space. It's a journey into one of the universe's most dynamic and unpredictable corners, a place where every discovery challenges what we think we know. Whether it's ghostly filaments that dance like cosmic cobwebs or shockwaves that accelerate particles to impossible speeds, the Crab Nebula is a reminder that the universe is far weirder, far wilder than we could ever imagine. And as we count down these 30 astonishing phenomena, you'll see why this celestial marvel continues to captivate, confuse, and inspire. So buckle up, we're about to explore a nebula that doesn't just defy expectations. It shatters them. At the very heart of the Crab Nebula, hidden within its swirling chaos, lies one of the most extreme objects in the universe, a pulsar spinning so fast it completes 30 revolutions every single second. This isn't just any dead star, it's a cosmic dynamo, a city-sized remnant of the supernova that gave birth to the nebula, packing the mass of our sun into a sphere no bigger than Manhattan. But what makes this pulsar truly bizarre isn't just its speed, it's the way it behaves. Most pulsars are like precision clocks, their spins steady and predictable. Not this one. Without warning, it suddenly slows down, speeds up, or unleashes violent energy bursts that baffle astronomers. These aren't minor hiccups. Some of these flares are so powerful they temporarily outshine the entire nebula, blasting out more energy in milliseconds than our sun produces in days. Scientists call these events glitches, but that word doesn't capture just how strange they are. Imagine a spinning top that randomly wobbles, slows, then lurches forward with enough force to send it flying across the room. That's essentially what's happening here, except the top weighs more than 1 billion tons. Even stranger, these glitches don't follow any clear pattern. Some theories suggest they're caused by cracks in the pulsar's crust, or by sudden shifts in its superfluid interior, a bizarre state of matter where particles flow without friction. But so far, no model fully explains why this particular pulsar misbehaves so dramatically. And then there's the radiation. The Crab Pulsar doesn't just emit the steady beams of radio waves typical of its kind. It's also a relentless source of gamma rays, the most energetic light in the universe, flaring unpredictably like a cosmic strobe light. Sometimes, these bursts are so intense they can be detected across thousands of light years, slamming into Earth's atmosphere with enough force to trigger satellite alarms. What's fueling these eruptions? One leading idea involves unimaginably strong magnetic fields, trillions of times more powerful than Earth's, twisting and snapping like rubber bands under extreme pressure. Yet even that doesn't account for all the pulsar's quirks. Every time researchers think they've figured it out, the Crab Pulsar throws another curveball. It's as if this tiny, ultra-dense star is actively defying the rules, challenging our understanding of how neutron stars should behave, and that's what makes it so fascinating. In a universe where most cosmic objects follow predictable patterns, this one is a rebel, a reminder that even in the cold depths of space, there are still mysteries waiting to be unraveled. Deep within the Crab Nebula's tangled depths, something even stranger than its erratic pulsar occurs: gamma-ray flares so powerful they rewrite the rules of high-energy physics. These aren't your typical cosmic outbursts. In mere minutes, the nebula can suddenly unleash gamma rays with energies exceeding 10 trillion electron volts, more than 100 billion times the energy of visible light. To put that into perspective, a single one of these flares carries enough punch to power every city on Earth for months. What's baffling isn't just their intensity, but their randomness. Unlike solar flares or pulsar glitches, which often show warning signs, these eruptions strike without any discernible pattern, vanishing as abruptly as they appear. The leading culprit, scientists suspect a process called magnetic reconnection, where the nebula's impossibly twisted magnetic field lines violently snap and realign like rubber bands stretched to their breaking point. These explosive rearrangements can accelerate particles to near light speeds in an instant, transforming the nebula into a natural particle collider far more powerful than anything humans could build. But here's the catch: even our best supercomputer simulations can't fully replicate the sheer scale of these events. The Crab Nebula's magnetic fields are so complex, so chaotic, that they behave unlike anything we've observed elsewhere in the universe. Then there's the wildcard theory. Could a hidden black hole be lurking within the nebula? Some researchers speculate that the original supernova might have left behind more than just a pulsar. If a small black hole orbits unseen, its gravitational pull could periodically shred passing gas clouds, creating sudden torrents of gamma rays. It's a radical idea, but not impossible. After all, we've detected similar, quiet black holes in other nebulae, yet the Crab keeps its secrets close. Every telescope trained on it, from Earth-based gamma-ray observatories to spaceborne X-ray detectors, has failed to pinpoint a definitive cause for these monstrous energy surges. What makes these flares truly unsettling is how they challenge decades of astrophysics. According to conventional models, such extreme particle acceleration should only happen near supermassive black holes or colliding galaxies, not in a relatively small, 1,000-year-old nebula. The Crab seems to break all the rules, operating with a ferocity that defies its size and age. And with each new flare, it taunts us, a cosmic reminder that for all our technology and theory, the universe still holds phenomena we can't yet explain. One thing's certain: until we solve this puzzle, the Crab Nebula will remain both a marvel and a mystery, shining brightly at the edge of our understanding. Amid the Crab Nebula's cacophony of gamma-ray flares and swirling magnetic storms, there's something far subtler at work, a ghostly chorus of radio waves so faint they've been nicknamed the nebula's whispers. Unlike the violent outburst from its pulsar, these signals are delicate, almost timid, drifting through space like cosmic static, but don't let their quiet nature fool you. These whispers are anything but ordinary. They pulse with a rhythm that doesn't match the nebula's other emissions, and their origin remains one of the most perplexing puzzles in modern astrophysics. Most cosmic radio sources, like pulsars or quasars, blast out signals with predictable intensity. The Crab's whispers, though, are erratic. They fade in and out, sometimes disappearing for days before resurfacing without warning. What's even stranger is their frequency structure. Instead of the clean, sharp lines typical of radio emissions, these waves are smeared, as if stretched or distorted by some unseen force. One theory suggests they're echoes of the pulsar's own radiation, scattered and warped by the nebula's labyrinth of magnetic fields. Imagine shouting into a cave and hearing your voice return as a dozen fragmented whispers, each bouncing off different walls. That might be what's happening here, but on a cosmic scale. Another possibility: these whispers could be the death rattles of electrons spiraling through the nebula's chaotic magnetic environment. When charged particles are accelerated, they emit radio waves, a process well documented in other cosmic objects. But in the Crab, something's off. The particles seem to lose energy in fits and starts, as though they're hitting invisible speed bumps in space. Some researchers propose that microscopic turbulence within the nebula, pockets of twisted magnetic fields no larger than a city, could be disrupting these particles' paths. It's like trying to drive a car down a road riddled with potholes. The ride becomes jerky, unpredictable. Then there's the wildest idea of all, that the whispers aren't coming from the nebula's known structures at all. Could there be hidden objects lurking in the Crab's depths, dim, cold remnants of the supernova that have eluded detection? A rogue planetesimal, a fragment of the original star's core, or even a previously unknown type of compact object could be stirring the nebula's magnetic soup, creating these faint but telltale ripples. Until we peer deeper into the Crab's radio spectrum with next-generation telescopes, the whispers will remain a tantalizing enigma. What makes these signals so revolutionary isn't just their mystery, it's how they force us to rethink the limits of radio astronomy. For decades, we've focused on the loud, dramatic emissions from space, the cosmic equivalents of fireworks. But the Crab's whispers remind us that the universe speaks in hushed tones too, and if we're not listening carefully, we might miss its most profound secrets. In a nebula already overflowing with wonders, these faint radio waves might just be the strangest phenomenon of all, because sometimes the quietest voices have the most to say. If you thought the Crab Nebula was just a static cloud of gas frozen in time, think again. Some of its most mesmerizing features are the delicate, thread-like filaments that weave through its expanse, structures that behave less like cosmic dust and more like living, breathing entities. Captured in stunning detail by the Hubble Space Telescope, these filaments aren't just beautiful, they're shockingly dynamic, shifting and reconfiguring at speeds that leave astronomers scratching their heads. One day, a tendril might stretch gracefully across the nebula. The next, it could twist into knots or vanish entirely, as if the nebula itself is rewriting its own anatomy. What makes these filaments so baffling is their speed. In most nebulae, gas moves sluggishly, reshaped over centuries by gentle stellar winds or distant gravitational tugs. But the Crab's filaments are different. Some race outward at over 1,000 kilometers per second, fast enough to cross the entire United States in less than 4 seconds. That's not just unusual, it's nearly impossible under conventional models. Normally, such violent motion would require an explosive force, like a nearby supernova or a jet from a black hole. Yet the Crab's filaments are dancing to their own rhythm, with no obvious driver behind their frenzy. One theory points to the pulsar's relentless energy. Like a cosmic mixer churning a pot of soup, the spinning neutron star's magnetic fields might be stirring the nebula's innards, creating whirlpools and shockwaves that whip the filaments into motion. But there's a problem. The filaments farthest from the pulsar move just as erratically as those near it, defying the logic that their energy should fade with distance. Another idea involves invisible magnetic ropes, tangled lines of force that snap and recoil, flinging gas outward like cracks in a whip. While simulations support this, they can't yet replicate the sheer variety of motions Hubble has documented. Then there's the eerie transparency of these filaments. Unlike typical nebula structures which glow steadily, the Crab's threads flicker unpredictably, brightening and dimming as if lit by a cosmic strobe light. Some researchers suspect ultra-fast electrons, accelerated by the pulsar, are zipping through the filaments like bullets, briefly energizing them before vanishing. Others propose that the filaments themselves are hollow bubble-like structures collapsing and reforming in real time. Hubble's time-lapse images reveal the true strangeness, filaments splitting like cell divisions, others merging like droplets of ink in water. It's a level of fluidity we'd expect from liquids, not rarefied gas in the vacuum of space. The Crab Nebula, it seems, doesn't just challenge our understanding of stellar death. It forces us to rethink how matter behaves in the most extreme environments. And with every new observation, these filaments whisper a tantalizing question. In a nebula where even the dust seems alive, what other laws of physics might be bending before our eyes? Beneath the Crab Nebula's dazzling light show lies a paradox that's kept astrophysicists up at night. A glaring mismatch between the energy pouring from its pulsar and the radiation we actually detect. In cosmic terms, it's like having a powerhouse generating enough electricity to light up a continent, yet only a single city grid flickers to life. The math is undeniable. The pulsar's spin-down energy, calculated from its gradual slowdown, suggests it should be emitting vastly more power than our telescopes observe. So where's all that missing energy going? The answer might rewrite our understanding of how dying stars fuel their aftermath. One leading hypothesis points to vast, invisible particle acceleration zones, regions where the nebula's tangled magnetic fields act like colossal slingshots, hurling electrons and protons to near light speeds. These particles could be carrying away the lost energy, but with a twist. Instead of emitting detectable light, they might be transforming it into other forms. Some could be escaping as ultra-high-energy neutrinos, ghostly particles that zip through matter undetected. Others might be fueling shockwaves beyond our current observational limits, like ripples in a pond we've only glimpsed one edge of. The challenge: these processes would occur in wavelengths or scales modern instruments struggle to capture, hiding in plain sight. Then there's the wild-card possibility of quantum effects at cosmic scales. The pulsar's intense magnetic field, trillions of times stronger than Earth's, might be bending the rules of particle physics itself. Quantum vacuum polarization, a phenomenon where empty space temporarily spawns particle-antiparticle pairs, could be siphoning energy away into a dimension we can't yet measure. It's not as far-fetched as it sounds. Lab experiments have observed similar effects in powerful magnetic fields, albeit on infinitesimally smaller scales. If happening in the Crab, this could explain why some energy vanishes without a trace. The most tantalizing clue comes from gamma-ray observations. Brief, ultra-high-energy flares, like those we've already explored, hint at reservoirs of pent-up energy suddenly being unleashed. These eruptions suggest the nebula isn't just losing energy, it's stockpiling it somewhere, like a cosmic capacitor charging until it bursts. Computer simulations reveal chaotic magnetic pockets where energy could accumulate, trapped like water behind a dam until turbulence breaches the barrier. But proving this requires telescopes capable of peering into the nebula's most turbulent regions at resolutions we've yet to achieve. What makes this energy discrepancy so revolutionary isn't just the gap in our equations. It's the implication that nebulae might operate like cosmic ecosystems, with energy cycling through hidden pathways much like nutrients in a rainforest. The Crab's pulsar could be seeding invisible processes that only manifest centuries later, or perhaps never in forms we're equipped to see. Until we develop tools to track these elusive energy flows, the nebula's missing power remains both a frustration and a beacon, guiding us toward discoveries that could redefine how we map the universe's hidden workings. Among the Crab Nebula's many mysteries, few are as visually striking as the eerie shadows that drift across its X-ray emissions, dark patches where the nebula's usual brilliance simply vanishes. These aren't empty regions or gaps in the gas. Instead, they act like cosmic silhouettes, as if something invisible is standing between the X-ray source and our telescopes, casting these ghostly outlines onto the nebula's glowing canvas. The strangest part: no known structure in the Crab should be dense enough to block such high-energy radiation. X-rays typically pierce through ordinary matter like sunlight through glass. Yet here they are, these persistent voids that defy every expectation. One leading theory suggests these shadows are the fingerprints of ultra-strong magnetic knots, twisted bundles of magnetic field lines so intense they bend the paths of X-ray producing electrons. Picture a highway where suddenly invisible barriers force speeding cars to swerve, leaving empty lanes behind. In this case, the cars are electrons spiraling along magnetic fields at near light speed, emitting X-rays as they go. If those fields become tangled enough, they could steer electrons away from certain trajectories, creating shadowy voids in the radiation we observe. Supporting this idea, some shadows align with regions where the nebula's magnetic field is predicted to be most chaotic. Yet simulations struggle to recreate shadows this pronounced, hinting that the real mechanism might be even wilder. Then there's the silhouette that refuses to stay put. Hubble and Chandra telescopes have tracked one particular shadow drifting across the nebula over years, moving at speeds no gas cloud should achieve without disintegrating. This isn't some static obstacle, it behaves like a solid object cruising through the nebula's heart. Could it be a fragment of the original star's core, a shard of ultra-dense matter surviving the supernova, or perhaps a temporary knot in the magnetic fabric, dense enough to scatter X-rays like a cosmic fog bank? The motion challenges both explanations, leaving researchers to wonder if they're seeing an entirely new class of astrophysical structure. The most tantalizing shadows appear near the pulsar itself, jagged, finger-like voids that ripple outward as if something is periodically shielding the X-ray glow. Some astronomers speculate these could be evidence of a debris disk, remnants of the shattered star swirling close to the neutron star. Others propose a more exotic idea: magnetic islands, self-contained loops of field lines that detach and reform like bubbles in boiling water, briefly trapping and redirecting particle flows. What makes these shadows so revolutionary isn't just their existence, it's how they reveal the invisible architecture of the nebula. Like feeling the shape of a keyhole in the dark, these X-ray absences let us map forces and structures no telescope can directly see. Every unexplained shadow whispers the same unsettling truth: the Crab Nebula is far more complex than its visible light suggests. Behind the veil of glowing gas, magnetic tempests rage, phantom structures drift, and particles dance to rules we've yet to decipher. Until we can peer deeper into these X-ray riddles, they'll remain both guides and gatekeepers pointing toward hidden layers of physics while guarding the crab's deepest secrets. Light from the Crab Nebula doesn't just glow, it dances with a hidden rhythm, a polarization pattern so bizarre it sent physicists back to their chalkboards. Polarization, the way light waves align as they travel, usually follows predictable rules in space, especially in environments where particles spiral around magnetic fields. But the crab, it scoffs at those rules. Instead of the orderly, symmetric polarization you'd expect from its swirling magnetic fields, the nebula's light arrives scrambled, as if someone took a cosmic comb to its waves and deliberately tangled them. Synchrotron radiation, the process where high-speed electrons corkscrew around magnetic lines, emitting light, should produce clean, uniform polarization. That's what we see in most pulsar wind nebulae. Yet here, the crab's light emerges with a patchwork of alignments, some regions polarized strongly in one direction, others weakly or not at all. It's like expecting the smooth stride of a marathon runner and instead witnessing a sprinter who keeps switching lanes mid-race. Even stranger, these polarization quirks shift over time, flickering like a faulty neon sign, with no clear connection to the pulsar's activity or the nebula's visible structures. One clue lies in the nebula's infamous magnetic chaos. While textbook models assume relatively orderly fields, the crabs are more like a bowl of spaghetti, twisted, knotted, and constantly rearranging. Electrons racing through this mess don't follow neat spiral paths. they're jostled unpredictably, emitting light waves that cancel each other's alignment. Think of it as trying to tune a radio while driving through a tunnel. The signal fractures into static. But simulations show even this turmoil can't fully explain the polarization's patchiness. There's something else warping the light, something we're not yet seeing. Then there's the wild card, quantum electrodynamics effects operating at scales we rarely observe. In extreme magnetic environments, like those near the Crab Pulsar, vacuum polarization, a quantum quirk where empty space itself becomes birefringent, could subtly twist the light's alignment. It's akin to how certain crystals split light into polarized beams, except here, the crystal is the fabric of space-time, warped by magnetic fields trillions of times Earth's. If confirmed, this would mark the first detection of such an effect in a natural cosmic setting, turning the Crab into a lab for testing quantum physics in ways no particle accelerator can match. What makes this polarization puzzle so transformative isn't just the challenge to existing models. It's the possibility that the Crab Nebula is revealing a new layer of magnetic behavior, one where fields don't just guide particles but actively imprint their chaos onto the very light we observe. Every scrambled photon carries a message. Our universe's most violent corners might not play by the tidy rules we've written. And until we untangle this knotted light, the Crab's polarization paradox will stand as both a frustration and a beacon, illuminating gaps in our understanding of how energy sculpts the cosmos. Amid the Crab Nebula's searing temperatures and violent energy surges, pockets of unexpected calm exist, regions so cool they defy logic. These cold spots aren't just slightly chilled. Some register temperatures hundreds of degrees lower than their surroundings, as if cosmic air conditioners were silently humming in the nebula's heart. What makes them truly baffling isn't just their presence, but their persistence. In an environment where shockwaves tear through space at millions of kilometers per hour and magnetic storms scramble particles to relativistic speeds, these frigid zones somehow hold their ground untouched by the chaos. One cluster of these cold spots appears near the nebula's outer filaments, where gas should theoretically be heated by the pulsar's relentless particle wind. Instead, spectroscopic readings reveal molecules like hydrogen cyanide and carbon monoxide compounds that normally shatter in high-energy environments. It's like finding ice cubes in a blast furnace. Astronomers first assumed these were fossil remnants of the original star's outer layers, preserved like cosmic freezer burn since the supernova explosion. But recent observations show some cold zones shifting position over years, proving they're not static relics but dynamic features with unknown origins. The leading theory involves magnetic shadows, localized regions where the nebula's tangled field lines act like insulating blankets, shielding gas from the surrounding particle storms. Picture a hurricane where certain streets remain eerily still because skyscrapers deflect the wind. Similarly, these magnetic fortresses might deflect the pulsar's energy barrage, creating temporary cold pockets. Supporting this, ALMA telescope data shows weak magnetic fields in these zones, correlating with their lower temperatures. Yet no model fully explains why some areas develop this insulation while identical-looking regions nearby roast under the pulsar's fury. Then there's the enigma of fast-moving cold clumps, dense knots of gas racing through the nebula at thousands of kilometers per second while staying stubbornly chilly. These shouldn't exist. Gas compressed at such velocities should heat up violently, like air in a bicycle pump, unless, as some theorists suggest, they're not gas at all. Could these be actual fragments of the progenitor star's icy mantle, surviving intact like boulders in a river? Or stranger still, might they be regions where dark matter, hypothetically left over from the supernova, interacts with normal matter to siphon away heat? Most perplexing of all are the cool cores, regions near the pulsar itself where temperatures plummet against all expectations. Normally, proximity to a neutron star means being bathed in lethal radiation. Yet Chandra X-ray Observatory has mapped zones mere light days from the pulsar where temperatures drop sharply. One radical paper proposes quantum vortexes in the pulsar's superfluid interior are somehow projecting cold fronts into the surrounding nebula like cosmic heat pumps running in reverse. Others argue these measurements aren't true cold spots at all, but artifacts of light being bent by the pulsar's extreme gravity in ways we don't yet understand. What makes these cool zones revolutionary isn't just their defiance of astrophysical norms, it's how they hint at unseen processes governing energy distribution in nebulae. Like shadows revealing the shape of invisible objects, these cold patches trace the outlines of forces we're only beginning to comprehend. Every unexplained temperature drop whispers the same tantalizing question. In a nebula where even the cold spots break the rules, what other thermodynamic surprises are waiting to be discovered? Deep within the Crab Nebula's turbulent expanse, astronomers have spotted something that shouldn't exist: tiny, dense clumps of material rocketing through space at nearly the speed of light. These aren't diffuse clouds or gentle streams of particles. They're cosmic bullets, compact masses hurtling so fast they could circle Earth 7 times in a single second. What's shocking isn't just their speed, it's how they maintain their shape. Ordinarily, gas traveling this fast would shred itself apart instantly, torn to ribbons by interstellar forces. Yet these bullets persist, streaking through the nebula like celestial shrapnel from some unseen explosion. Their composition holds the first clue to their resilience. Spectroscopy reveals these bullets are rich in heavy elements: iron, silicon, and neon, likely forged in the original star's heart before its explosive death. Unlike the nebula's wispy hydrogen clouds, these dense metallic knots can withstand the extreme forces that would vaporize lighter material. Imagine the difference between throwing a snowball and a lead pellet into a hurricane. One disintegrates instantly while the other punches through. But even this doesn't fully explain their survival. At these velocities, collisions with even sparse nebula gas should erode them over time. Yet Hubble images show some bullets traveling unscathed for decades, their paths etching straight lines through the chaos. The leading theory involves magnetic armor. These clumps might be encased in self-generated magnetic fields, wrapping them in protective shells that deflect incoming particles. It's a phenomenon observed in lab plasmas, where magnetic bottles can stabilize high-speed matter. In the Crab, the bullet's motion through the nebula's own magnetic web could induce these shielding fields, creating a feedback loop that reinforces their structure. Supporting this, radio telescopes detect faint synchrotron halos around some bullets, a telltale sign of electrons spiraling along magnetic barriers. Then there's the mystery of their acceleration. Most nebula material moves at a fraction of light speed, pushed gradually by the pulsar's wind. These bullets defy that pattern, suggesting they were launched by a singular, cataclysmic event. One possibility: the pulsar's birth might have been even more violent than we thought. When the original star collapsed, asymmetrical shockwaves could have focused energy into narrow jets, propelling these fragments like buckshot from a cosmic shotgun. Alternatively, magnetic reconnection events, those explosive rearrangements of field lines, might act as slingshots, sporadically flinging dense clumps to relativistic speeds. The most perplexing bullets, however, are those moving sideways relative to the pulsar's spin axis. Conventional models insist ejecta should align with the neutron star's rotation, yet these outliers carve paths at odd angles. Some researchers speculate they're relics of the progenitor star's pre-collapse structure, perhaps chunks of its inner disk flung outward during the supernova's asymmetrical detonation. Others propose they're evidence of a companion star shredded during the explosion, its remnants now ricocheting through the nebula. Every unanswered question about these bullets underscores a deeper truth. The Crab Nebula isn't just a static aftermath of a stellar death. It's an active crime scene with pieces of evidence still flying through space at unimaginable speeds, and each one carries forensic clues locked in its elemental makeup, its trajectory, its defiance of destruction, that could rewrite the story of how stars die and nebulae are born. Until we track them all, the full history of the Crab's explosive birth remains tantalizingly out of reach. While the Crab Nebula dazzles in visible light and X-rays, its infrared emissions tell a stranger story, one where the glow doesn't just fluctuate, but does so in ways that defy conventional physics. Unlike the steady pulsar-driven light show we see in other wavelengths, the nebula's infrared output rises and falls unpredictably, sometimes brightening by up to 20% in mere weeks before fading just as quickly. What's bizarre isn't the variability itself, it's that these shifts don't correspond to changes in the pulsar's activity or the nebula's visible structures. It's as if an invisible hand is dialing up and down the heat on cosmic dust we can't even see. At the heart of this mystery lies the nebula's dust, fine particles of carbon and silicates born from the supernova's aftermath. Normally, such dust should glow steadily when warmed by nearby radiation, like embers in a campfire. But the Crab's dust behaves more like a campfire where some embers suddenly flare white-hot while others inexplicably cool. The Spitzer Space Telescope captured this anomaly in detail, revealing patches of dust that heat to over 1,000 degrees Celsius, far hotter than the pulsar's radiation alone can explain before cooling just as rapidly. One theory suggests microscopic quantum dots, tiny crystalline structures within the dust, might be absorbing and releasing energy in erratic bursts. These nanoscale marvels, known to exhibit unusual thermal properties in lab settings, could be turning the nebula's dust into a cosmic capacitor, storing and discharging energy in fits and starts. Then there's the eerie synchrony. Despite the nebula's vast size, infrared flares sometimes ripple across light years of space in coordinated patterns, as if some unseen wave is passing through. Traditional shock waves move too slowly to explain this, leading researchers to propose a radical idea. The dust might be interconnected by a web of magnetic filaments, acting like a single nervous system where a signal triggers cascading heating events. Imagine a field of dominoes where knocking one over makes others light up instead of fall. That's the kind of bizarre coupling we might be seeing here. The most tantalizing possibility, these fluctuations could be evidence of vacuum polarization, a quantum effect where space itself momentarily becomes conductive near ultra-strong magnetic fields. If occurring in the Crab's turbulent heart, this process might briefly energize dust grains like popcorn in a microwave, creating infrared spikes unrelated to any external radiation source. It's a hypothesis that blurs the line between astrophysics and quantum mechanics, suggesting the nebula isn't just a celestial object but a natural laboratory for testing some of science's most abstract theories. What makes these infrared quirks so revolutionary isn't just their defiance of expectations, it's how they expose the hidden life of cosmic dust. Once considered little more than passive debris, the Crab's dust is now revealing itself as an active player in the nebula's energy drama, capable of behaviors we've yet to fully catalogue. And with every unpredictable flicker, it reminds us that even the quietest corners of the cosmos can harbor the wildest surprises. One of the most surreal phenomena in the Crab Nebula isn't happening in real time. It's a delayed replay of events that unfolded nearly 1,000 years ago. Light echoes, the ghostly afterimages of the original supernova explosion, ripple through the nebula like reflections in a funhouse mirror, showing us the same cataclysm from multiple angles across centuries. These aren't mere optical illusions. They're physical proof that light takes time to travel, bouncing off dust clouds at different distances and arriving at Earth decades or even centuries apart. Imagine watching a firework explode, then seeing its flash reflected off buildings around you seconds later, except in this case, the buildings are interstellar dust clouds light years apart, and the firework is a star's violent death. The most stunning example appeared in 2007, when astronomers spotted an arc of light expanding outward from the nebula's center at an impossible speed. This wasn't a physical structure moving faster than light. It was a light echo, the flash from the 1054 supernova finally reaching a distant dust cloud and scattering toward Earth. By tracking its motion, researchers reconstructed the original explosion with unprecedented detail, revealing asymmetries in the blast that no historical records could capture. But here's where it gets eerie. Other echoes continue arriving today, each one a fragmented glimpse of the supernova as seen from a different cosmic vantage point. It's like piecing together a shattered stained glass window where every fragment shows the same event through a slightly distorted lens. What makes these echoes scientifically invaluable is their forensic detail. Unlike the nebula's modern glow, which blends nearly a millennium of stellar debris and pulsar energy, light echoes carry pristine spectral fingerprints from the explosion's first moments. Recent analyses revealed unexpected chemical signatures, traces of titanium and nickel that suggest the progenitor star's core collapse was even more turbulent than models predicted. Some echoes even show polarized light, hinting at magnetic fields that shaped the explosion's earliest shockwaves. This data is rewriting textbooks, proving that supernovae aren't symmetric fireballs but chaotic, lopsided events where dying stars literally tear themselves apart unevenly. The real mind-bender, some of these echoes haven't even reached us yet. Dust clouds farther out in the nebula's halo will continue reflecting the supernova's light for centuries to come, creating a cosmic time capsule that future astronomers will study. It's as if the universe engineered its own delayed broadcast system, ensuring no single generation could monopolize the story of the crab's birth. And with every newly detected echo, we're not just observing history, we're stepping into a celestial hall of mirrors where the past refuses to fade quietly into the dark. The Crab Nebula holds another enigma that has particle physicists leaning forward in their seats, an inexplicable surplus of antimatter, specifically positrons, zipping through its chaotic interior. Normally, when matter and antimatter meet, they annihilate in bursts of energy. But here, positrons, the antimatter counterparts to electrons, aren't just surviving, they're thriving in numbers that defy conventional astrophysical models. Detectors on Earth have picked up their signals for decades, with positron counts up to 10 times higher than expected, as if the nebula were harboring a hidden antimatter factory. What makes this positron excess so puzzling isn't just their abundance, it's their energy spectrum. Unlike the smooth distribution seen in other cosmic accelerators, the Crab's positrons arrive with a jagged, uneven profile, clustering at specific energy levels like notes in a dissonant chord. One theory points to the pulsar's furious spin, which could be generating cascades of electron-positron pairs as its magnetic fields twist and snap. In this scenario, the pulsar acts like a colossal particle collider, accelerating matter to energies where spontaneous pair production occurs. But simulations show this process should create equal parts electrons and positrons, not the lopsided surplus we observe. Then there's the wildcard possibility of dark matter decay. Some exotic particles predicted by theoretical physics, like neutralinos, could break down into positrons as they interact with the nebula's extreme environment. If true, the Crab might be giving us a front-row seat to processes usually hidden in the universe's darkest corners. Yet even this bold idea struggles to explain why the positron excess isn't uniform, why certain regions of the nebula seem to be leaking antimatter like a sieve while others show barely a trace. The most tantalizing clue comes from the positron's trajectories. Some appear to spiral outward from deep within the nebula's filaments, not the pulsar itself, suggesting unseen structures. Perhaps magnetic vortices or collapsing shock fronts are acting as secondary accelerators. It's akin to discovering a network of invisible particle cannons scattered across a battlefield, each firing antimatter in unpredictable bursts. What's clear is that the Crab's antimatter mystery isn't just a curiosity. It's a challenge to our understanding of how energy and particles behave in extreme environments. Every unexpected positron forces us to reconsider whether we're witnessing known physics pushed to its limits or something entirely new. And until we crack this puzzle, the nebula's antimatter surplus remains a cosmic question mark, written in the fleeting trails of particles that shouldn't exist in such numbers, but undeniably do. Hidden among the Crab Nebula's swirling filaments are fleeting anomalies that challenge our understanding of cosmic erosion. Dense knots of gas, some as massive as Earth's oceans, that vanish without warning. These aren't gradual dissipations. One moment they're clear in telescope images, glowing stubbornly against the nebula's chaos. The next they're gone, leaving behind ghostly outlines where matter once thrived. The most baffling disappearances happen in regions with no obvious destructive forces, no pulsar wind, no shockwaves, as if the knots simply dissolve into the void. The leading explanation involves a process called thermal evaporation, where intense radiation boils away the knots' outer layers faster than telescopes can track. In most nebulae, this happens slowly over centuries, but the Crab's radiation field is so fierce that simulations suggest it could strip atomic layers from these clumps in mere months, like sunlight vaporizing morning dew. Supporting this, Hubble has caught knots shrinking at record speeds, their edges blurring as gas turns to plasma. Yet some vanish too quickly even for this mechanism, suggesting something far stranger at work. One particularly dramatic event in 2012 saw a knot 30 times Earth's mass disintegrate in under 6 weeks. Its spectral signature, rich in oxygen and neon, implied it was a surviving fragment of the progenitor star's deep interior. Such heavy elements should resist evaporation, yet this knot shattered like glass under a hammer. Researchers now suspect magnetic reconnection events, those explosive rearrangements of field lines, might be delivering knockout blows to already weakened knots. Imagine a sandcastle hit by a rogue wave. The structure was already fragile, but the final collapse comes suddenly and completely. Then there's the enigma of the phantom knots, structures that vanish not just from visible light but from all wavelengths simultaneously. These aren't cases of gas cooling or shifting emission lines. They're total erasures, as if someone flicked a cosmic switch. One theory proposes rapid collapse into exotic states of matter. Under extreme pressure, the knot's cores might reach densities where neutrons dissolve into quark-gluon plasma, a state so dense it stops interacting with light entirely. It's speculative but not impossible. Similar conditions are briefly created in particle colliders. If happening naturally in the Crab, it would mark the first observed case of quark nova, a hypothesized phenomenon where ordinary matter transitions into something utterly alien. The most unsettling disappearances hint at unseen gravitational influences. A few knots exhibit telltale spiraling motions before vanishing, as if being sucked into an invisible drain. While no black hole has been detected in the Crab, some models suggest microscopic primordial black holes left over from the early universe could lurk within the nebula, their tiny event horizons swallowing matter too stealthily for telescopes to catch. Others argue these motions could stem from dark matter clumps, their gravity tugging briefly on visible gas before both vanish beyond detection. Every vanished knot leaves behind more questions than answers. Are we witnessing mundane destruction or the birth of new states of matter? Do these events recycle material into the nebula's ecosystem, or do they shunt it into some unseen dimension of physics? The Crab Nebula, ever the cosmic trickster, refuses to show its hand, only the empty spaces where its secrets briefly flickered into view. The Crab Nebula's magnetic fields don't just bend the rules, they tie them into knots. Imagine a ball of yarn after a cat's finished with it, loops and tangles crossing at chaotic angles, defying every attempt to smooth them out. That's the state of magnetism in this cosmic storm, where field lines twist into configurations so complex they shouldn't exist under known physics. Most celestial magnetic fields organize themselves into tidy patterns, like the symmetrical spokes of a bicycle wheel. But here, they're more like a Jackson Pollock painting splattered across space in frenzied, unpredictable swirls that somehow hold their shape against forces that should shred them apart. Recent observations from the Chandra X-ray Observatory reveal these magnetic knots aren't just superficial quirks. Some stretch light years across, their tangled structures remaining stable for decades despite the nebula's violent particle winds. It's as if space itself has developed a way to tie permanent knots in its own fabric, structures that refuse to unravel even when bombarded by energy equivalent to 1,000 suns. The most perplexing examples form near the pulsar, where magnetic field lines coil around each other like braided steel cables, except these cables are made of pure energy, thinner than an atom yet strong enough to steer entire plasma currents. Traditional models of magnetohydrodynamics, the science of how magnetic fields and plasma interact, predict such complex tangles should dissipate in seconds. Yet in the crab they persist, sometimes even growing more intricate over time. One theory suggests quantum effects might be at play. At scales smaller than an atom, the field lines could develop microscopic kinks that act like Velcro, locking the tangles in place. Another idea points to the nebula's relativistic particle soup, where electrons moving at near light speeds create feedback loops that reinforce the chaos rather than smoothing it out. Picture stirring cream into coffee, only to watch the swirls grow sharper instead of fading. That's the level of defiance we're dealing with. The real shock came when researchers mapped these tangles in 3 dimensions using polarization data. Instead of lying flat like ribbons on a gift box, the field lines corkscrew through space in fractal patterns, repeating their tangled designs at every scale from light years down to kilometers. This self-similarity hints at an underlying order within the chaos, a hidden mathematical rule governing how the nebula's magnetism organizes itself. Some scientists compare it to turbulence in fluid dynamics, where eddies form within eddies ad infinitum. But magnetism isn't supposed to behave this way, especially not in an environment where particles race past each other at nearly the speed of light. Perhaps the most revolutionary implication lies in what these tangles mean for energy transfer. Normally, magnetic fields channel energy smoothly, like wires conducting electricity. But the crab's knotted fields might work more like a maze, trapping energy in some regions while funneling it explosively to others. This could explain why certain parts of the nebula flare unpredictably while adjacent zones remain eerily calm. The magnetic tangles are acting like cosmic traffic jams, redirecting particle flows in ways no simulation can yet predict. Every twisted field line in the Crab Nebula whispers a tantalizing question. Are we seeing a glitch in nature's code, or a feature we've simply failed to recognize until now? As telescope technology advances, allowing us to probe these magnetic labyrinths in greater detail, one thing becomes clear: the universe's rulebook for magnetism has chapters we haven't even begun to read. And the crab, ever the patient teacher, is holding them just out of reach, waiting for us to decipher its tangled lessons. Stretching far beyond the Crab Nebula's visible boundaries lies an eerie, faint glow, a gamma-ray halo so vast it dwarfs the nebula itself, extending nearly 100 light-years into space. This ghostly ring shouldn't exist, at least not according to our best models of pulsar winds. Theories predict that the pulsar's high-energy particles should lose their punch long before reaching such distances, fading into the interstellar void. Yet here it is, a whisper-thin shroud of gamma rays wrapping the crab like a cosmic veil, pulsing with energies that defy conventional physics. What makes this halo so perplexing isn't just its size, it's the way it flickers. Unlike the steady gamma-ray glow from other pulsar wind nebulae, the crab's halo brightens and dims in sync with the pulsar's rotation, as if the entire structure is wired directly to the neutron star's heartbeat. That's impossible under classic particle diffusion models, which assume it would take centuries for particles to travel that far. Instead, this synchronization suggests something extraordinary. The nebula's magnetic fields might be acting like interstellar highways, funneling particles at near light speed across unimaginable distances without losing coherence. Picture throwing a pebble into a pond and watching the ripples instantly reach the shore, a violation of physics unless the water itself is somehow prearranged to transmit the shock. The halo spectrum deepens the mystery. Most gamma-ray emissions from pulsars show a smooth drop-off at high energies, like a dimmer switch gradually turned down. But the Crab's halo has jagged peaks, with certain energy levels shining far brighter than others. Some researchers speculate these spikes could be evidence of particle acceleration happening not just at the pulsar, but throughout the halo itself, as if invisible boosters are scattered across space, re-energizing electrons like cosmic relay stations. Others propose a wilder idea: quantum fluctuations in the vacuum of space, amplified by the nebula's extreme magnetic fields, might be generating gamma rays directly, bypassing traditional particle acceleration entirely. Then there's the halo's asymmetry. Most of its gamma rays cluster on one side of the nebula, forming a lopsided crescent that shifts position over years. This could hint at an unseen gravitational influence, perhaps a nearby black hole or dark matter clump warping the particle flows. Or it might trace back to the original supernova explosion, which could have blasted debris unevenly into space, leaving behind density variations that still sculpt the halo's shape today. Every unanswered question about this gamma-ray wraith forces us to reconsider how energy propagates through space. The Crab's halo isn't just a curiosity, it's a challenge, proving that even in death, stars can reshape our understanding of the universe's most fundamental rules. And until we unravel its secrets, this ghostly glow will linger at the edges of our knowledge, a silent reminder of how much we have yet to learn. Among the Crab Nebula's countless peculiarities, few are as quietly revolutionary as the spectral lines that refuse to stay put. When astronomers train their spectrographs on the nebula's glowing gases, they expect to see the familiar fingerprints of elements hydrogen, oxygen, sulfur, each emitting light at precise, unshakable wavelengths. But the Crab laughs at expectations. Its spectral lines dance unpredictably, shifting positions like mirages on a highway, hinting at gas motions so violent they defy measurement, or perhaps something even stranger, altering the very rules of atomic physics. These shifts aren't subtle. Some lines wobble back and forth like pendulums, their wavelengths stretching and compressing as if the gas itself is breathing. Others fracture into multiple peaks, revealing velocities within the nebula that range from near standstill to half the speed of light, all within the same pocket of space. The most extreme cases show oxygen emission lines displaced so far they initially masqueraded as unknown elements, tricking researchers into false discoveries. Traditionally, such displacements signal gas moving toward or away from us, a concept called Doppler shifting. But in the Crab, these motions are too chaotic, too contradictory, to be explained by simple bulk movement. It's like watching a choir where every singer belts notes at random pitches, yet somehow produces a symphony. One theory blames shock surfing, particles caught in cascading shockwaves that ricochet through the nebula's tangled magnetic fields. These shocks could accelerate atoms to different velocities in microseconds, creating a jumbled spectral fingerprint. Supporting this, Hubble has captured filaments where gas on one side races toward Earth while the other side flees, as if a cosmic tornado tore through. Yet even this can't account for spectral lines that shift asymmetrically, with one side of the peak stretching farther than the other. Such distortions suggest quantum effects normally masked in calmer environments like stark broadening, where intense electric fields smear electron energy levels. Then there's the enigma of the phantom shifts, spectral lines that change positions when observed at different timescales. over months certain lines drift steadily, tracing slow gas flows. But when measured in minutes, the same lines jitter erratically, as if atoms are teleporting between locations. Some researchers propose this could be evidence of vacuum polarization, where the pulsar's monstrous magnetic field momentarily warps the quantum vacuum around atoms, tweaking their emission frequencies. It's a phenomenon so exotic it's typically only discussed in theoretical papers about neutron star atmospheres. The most tantalizing shifts occur in the nebula's quietest zones, regions with no visible turbulence. Here, spectral lines slide smoothly to longer wavelengths, as if space itself is expanding locally. Could these be Einstein shifts, gravitational redshift from dense, invisible objects like quark nuggets or primordial black holes hiding in the gas? Or might they reveal a deeper truth that in the crab's extreme environment, even the constants of nature, like the speed of light or electron charge, flicker at scales we're only beginning to probe? Every wandering spectral line whispers the same unsettling truth. The Crab Nebula isn't just a physical puzzle. It's a quantum funhouse where atoms behave like carnival mirrors, distorting reality in ways that challenge our most fundamental assumptions. And until we decode their spectral sleight of hand, these shifting lines will remain both a frustration and a beacon pointing toward physics we've yet to imagine. In the heart of the Crab Nebula's radiation maelstrom, where temperatures typically soar to millions of degrees, there exists a population of cosmic outliers, dust particles that stubbornly refuse to warm up. These frozen grains, some no larger than smoke particles, hover at temperatures barely above absolute zero despite being immersed in the pulsar's relentless energy bath. It's like finding ice cubes floating unscathed in lava, a thermal paradox that challenges one of physics' most fundamental principles, the law of thermal equilibrium. Normally, objects exposed to intense radiation should absorb energy until they match their surroundings. Yet these dust motes remain eerily chilled, as if shielded by some invisible refrigeration system. The mystery deepens when you examine their composition. Spectroscopic analysis reveals these ultra-cold grains are rich in carbon, much like soot from a candle flame. But unlike ordinary carbon dust, their atomic structure appears riddled with microscopic imperfections, tiny voids and lattice irregularities that might act like thermal mirrors, deflecting incoming radiation instead of absorbing it. Picture a house with walls made of broken glass. Sunlight passes through without warming the interior. Similarly, these structural flaws could be scattering the pulsar's high-energy photons, preventing energy absorption. Some laboratory experiments with nanostructured carbon support this idea, showing similar heat-defying properties under extreme conditions. Yet even this doesn't fully explain the grain's persistent chill, as calculations suggest they should still warm gradually over time. Then there's the even stranger subset of particles that actually cool down when exposed to more radiation, a thermal response akin to metals shrinking when heated instead of expanding. Researchers speculate these might be experiencing quantum levitation, where the pulsar's magnetic fields lock the dust grains in place while allowing high-energy electrons to skim past without transferring energy. It's an effect observed in superconductors on Earth, but never before imagined at cosmic scales. If confirmed, it would mean the Crab Nebula is inadvertently conducting the universe's largest quantum physics experiment, with these dust grains as unwitting participants. The most perplexing cold dust clusters near the pulsar's polar jets, where radiation is most intense. Here, temperatures plummet to mere degrees above absolute zero, creating frosty islands in a plasma sea. One radical theory suggests these zones might harbor Bose-Einstein condensates, exotic states of matter where atoms coalesce into a single quantum wave. Normally requiring lab conditions colder than deep space to form, these condensates could theoretically arise in the Crab if magnetic fields suppress particle motion enough to trigger quantum condensation. It's a long shot, but not impossible, and if real, it would mean these humble dust grains are exhibiting quantum behavior visible from thousands of light years away. What makes these frozen particles so revolutionary isn't just their defiance of thermodynamics. They're forcing us to reconsider how energy interacts with matter in extreme environments. Every chilly grain whispers a tantalizing possibility that the universe has secret methods of heat management we've yet to comprehend, and the Crab Nebula, ever the cosmic rebel, is proudly demonstrating them for all who care to look. Even amid the Crab Nebula's constant flickers and flares, nothing prepares astronomers for its most jarring phenomenon. The entire nebula occasionally ignites in a synchronized surge of brightness, as if someone turned up a cosmic dimmer switch. These aren't localized outbursts or pulsar glitches. For minutes to hours, the nebula's entire visible structure, filaments, core, and outer tendrils flashes dramatically brighter, emitting up to 20% more light across all wavelengths simultaneously. It's like watching a city's skyline suddenly double in luminosity, every building flaring in perfect unison, then fading back to normal just as mysteriously. The first recorded instance occurred in April 2011, when telescopes worldwide caught the Crab's gamma-ray output spiking violently. At first, researchers assumed it was another pulsar flare. But as data rolled in, the truth became undeniable. X-rays, visible light, even radio waves all flared in lockstep, a coordinated brightening spanning light years. No known celestial object behaves this way. Supernova brighten gradually, pulsars flicker erratically, but for an entire nebula to light up at once. That suggests a unified trigger, something capable of energizing every particle across vast distances nearly instantaneously. One explanation points to the nebula's magnetic web. If a massive reconnection event occurred, think of a cosmic short circuit where magnetic field lines snap and realign. It could unleash a tsunami of energy rippling through the entire structure. Simulations show such an event might briefly supercharge electrons nebula-wide, making them emit more light everywhere at once. But there's a catch. The brightening events lack the telltale X-ray spikes typical of magnetic reconnection. Instead, the light rises smoothly, almost as if the nebula's entire energy baseline has been temporarily cranked higher. Another theory ventures into exotic physics. Quantum vacuum fluctuations, normally too subtle to notice, might become amplified in the Crab's extreme magnetic environment. If space itself briefly became more conductive, a phenomenon predicted but never observed, it could allow the pulsar's energy to flood the nebula more efficiently, like a dam's gates opening wide. This would explain the synchronized brightening without requiring particles to be individually zapped. It's a fringe idea, but the Crab has never been shy about bending the rules. The most perplexing brightening event happened in March 2017, when the nebula's glow didn't just intensify, it changed color. Normally blue-white filaments shifted toward violet, a spectral tweak implying electrons suddenly gained energy without any increase in speed. It's as if the particles themselves became temporarily more efficient at emitting light, a behavior with no precedent in astrophysics. Some researchers wonder if this hints at collective quantum effects, where electrons behave more like a unified wave than individual particles. Laboratory plasmas exhibit similar traits under rare conditions, but never at interstellar scales. Every synchronized flare from the Crab Nebula forces a humbling realization: we're still novices at reading the universe's playbook. This nebula doesn't just push boundaries, it casually strolls past them, leaving us scrambling to catch up. And with each unexplained brightening, it offers a tantalizing glimpse of physics operating in modes we've yet to name, let alone understand. Deep within the Crab Nebula's turbulent heart, a population of rogue electrons races through space with impossible energy, each packing enough punch to outshine a small star. These aren't your garden-variety cosmic particles. Measurements show they're revved up to energies surpassing 1,000 trillion electron volts, far beyond what even the pulsar's formidable acceleration should allow. It's as if nature's particle accelerator got stuck on overdrive, churning out electrons that break all the rules of astrophysical speed limits. The mystery lies in the numbers. Based on the pulsar's spin-down energy and known physics, scientists calculated how many ultra-high-energy electrons the nebula should host. Yet actual observations reveal a staggering surplus, up to 10 times more than predicted, like finding a packed stadium where the tickets sold only accounted for a few hundred attendees. These overachieving electrons cluster in strange ways too, forming dense pockets near shock fronts where conventional models say they should thin out. Some even appear to gain energy after passing through regions that should drain them, like marathon runners who sprint faster after climbing a mountain. One possible explanation involves the nebula's chaotic magnetic fields acting like cosmic pinball machines. Electrons could be ricocheting between magnetic mirrors, regions where field lines compress and rebound particles, gaining energy with each collision. This Fermi acceleration process is well documented in other cosmic environments, but in the Crab, it seems to operate with freakish efficiency. Recent simulations suggest the magnetic knots we explored earlier might be key, their tangled geometries providing perfect conditions for electrons to surf on cascading shockwaves indefinitely. Imagine a surfer catching not just one wave but an endless chain of perfect curls, each one boosting their speed beyond reason. Then there's the wildcard theory, quantum vacuum breakdown. Near the pulsar's surface, magnetic fields reach such intensities that they could spontaneously create electron-positron pairs from empty space itself. This process, predicted by quantum electrodynamics but never conclusively observed in nature, might be flooding the nebula with born energetic particles that skip traditional acceleration entirely. Supporting this, some high-energy electron beams appear to originate from seemingly empty voids in the nebula regions, with no visible shock fronts or magnetic structures to explain their presence. The real enigma emerges when examining these electrons' lifespans. At such extreme energies, they should lose power rapidly by radiating gamma rays, fading to mundane levels within days. Yet many persist for years, their energy signatures remaining stubbornly high. This suggests hidden refueling stations scattered through the nebula, perhaps undiscovered magnetic reconnection sites or turbulence zones where particles siphon energy from the pulsar wind like cosmic vampire bats. What makes this electron overpopulation so revolutionary isn't just the particles themselves, but what they imply about energy transfer in extreme environments. The Crab Nebula appears to harbor acceleration mechanisms we've yet to imagine, processes that could rewrite our playbook for how cosmic rays are born. And until we crack this puzzle, these rogue electrons will keep racing through the nebula's veins, a high-energy mystery written in the trails of particles that refuse to play by the rules. Amid the Crab Nebula's cacophony of gamma-ray flares and magnetic storms, there's an unexpected harmony, a chorus of low-frequency plasma waves resonating through its depths like the haunting hum of a distant choir. These rhythmic oscillations, detected by radio telescopes as subtle ripples in the nebula's electromagnetic field, pulse with eerie regularity, some repeating every few minutes with the precision of a metronome. Dubbed singing waves by researchers, they're not random noise but structured vibrations, as if the nebula itself were breathing in slow, measured sighs. What makes these waves extraordinary is their origin. Plasma, the superheated, electrically charged gas filling the nebula, normally produces chaotic, turbulent waves when stirred by magnetic fields or shock fronts. Yet here, the oscillations emerge with almost musical coherence, their frequencies harmonizing in ways that suggest an unseen conductor orchestrating the chaos. Some waves spiral outward from the pulsar like the grooves of a cosmic record, while others crisscross filaments like standing waves in a vibrating string. The most mesmerizing examples form interference patterns, where overlapping waves create zones of amplified crescendos and near-silent rests. Sculpting the nebula's energy flows into an intricate soundless symphony. One theory points to the pulsar's relentless particle wind as the maestro. As this stream of high-energy particles slams into slower-moving nebula gas, it could generate shock fronts that reflect off magnetic boundaries, creating resonant cavities where waves bounce and reinforce one another. Think of it as blowing across the mouth of a bottle. The container's shape determines the pitch. In the crab's case, its complex magnetic architecture might be acting like a celestial organ pipe, tuning plasma vibrations into discrete notes. Spectrographic analysis reveals these notes cluster around frequencies reminiscent of Earth's own ultra-low-frequency radio waves, the same range used by whales to communicate across oceans, though here scaled up to cosmic proportions. Then there's the mystery of the missing harmonics. Mathematical models predict the nebula should produce a full spectrum of overtones, yet observations show glaring gaps. Certain expected frequencies simply don't appear. Some researchers speculate this could hint at hidden structures absorbing specific vibrations, like acoustic panels in a concert hall. Others propose a wilder idea. Quantum effects in the plasma might be forbidding certain wave modes, a phenomenon observed in lab-created quark-gluon soups but never before in space. If true, the crab's plasma could be offering us a front-row seat to quantum behavior playing out across light years. The most profound implication lies in how these waves sculpt the nebula's evolution. Unlike sound waves in air, plasma waves carry electric and magnetic forces capable of nudging particles over vast distances. Simulations suggest the singing waves might be shepherding dust grains into dense clusters, explaining some of the nebula's peculiar filament patterns, or even gently steering cosmic rays toward escape routes. It's a revelation that repositions plasma waves from passive curiosities to active architects, quietly shaping one of the universe's most dynamic structures through their persistent rhythmic push. Listening to these cosmic vibrations, one can't help but wonder, is this how the universe sings itself into shape? In the Crab Nebula's case, the answer seems to be a resonant yes, a reminder that even in the vacuum of space, there's music if you know how to listen. And every harmonic ripple carries clues not just about this nebula, but about the hidden symphonies awaiting discovery in the countless stellar cathedrals dotting the cosmos. The Crab Nebula's shockwaves should act like cosmic speed limits, violent fronts where particles gain energy but never exceed certain velocities. Yet somehow, sprinkled throughout its chaos, are rebellious electrons and protons racing faster than these shocks could possibly produce. It's as if these particles have stolen energy from some unseen source, leaving physicists to wonder, what kind of celestial drag race is happening inside this nebula? Take the nebula's outer filaments, where particles have been clocked at 99.9% the speed of light, far swifter than the local shockwaves can account for. Traditional acceleration models rely on a process called diffusive shock acceleration, where particles bounce back and forth across shock fronts like pinballs, gradually gaining speed. But in the Crab, some particles appear to skip the gradual part entirely, rocketing straight to relativistic velocities in one explosive jump. Imagine a car accelerating from 0 to 60 in a fraction of a second without pressing the gas pedal. That's the level of defiance we're seeing. One clue lies in the particles' trajectories. High-resolution observations show many of these speed demons spiral along magnetic field lines with peculiar kinks, sharp bends that shouldn't exist in smooth, well-ordered fields. These kinks might be the smoking gun. Simulations suggest that when magnetic field lines snap and reconnect, they can create microscopic twist points that act like slingshots, launching particles to extreme speeds almost instantaneously. It's the difference between pushing a swing gently and yanking the chain with all your might. The latter delivers a violent burst of energy no steady push could match. Then there's the mystery of the backwards particles. A subset of these high-speed rebels actually move against the nebula's dominant particle wind, like salmon swimming upstream in a hurricane. This makes no sense unless something is accelerating them locally, independent of the pulsar's main energy flow. Some researchers speculate hidden magnetic vortices swirling eddies in the nebula's plasma could be acting as natural particle colliders, revving up particles in isolated pockets. Others point to the nebula's famous gamma-ray flares, wondering if their leftover energy might linger in unseen forms, waiting to boost passing particles like cosmic trampolines. The real curveball comes from the particles' energy signatures. At certain wavelengths, their radiation spikes match predictions for a process called direct electric acceleration, where particles surf on waves of pure voltage, something rarely observed outside laboratory plasmas. If confirmed, it would mean the Crab Nebula has spontaneously built the universe's most powerful natural particle accelerator, operating on principles we've barely begun to understand. Every overachieving particle in this nebula forces a humbling admission. Our models for cosmic acceleration are incomplete. The Crab isn't just bending the rules, it's rewriting them in real time, showing us frontiers of physics we didn't know existed. And until we decode how these particles cheat the cosmic speed limit, they'll keep racing through the nebula's veins, leaving nothing but unanswered questions in their wake. Buried within the Crab Nebula's radio emissions lies one of its most elusive features: delicate, thread-like jets that materialize only in certain wavelengths before vanishing like cosmic mirages. These ghostly structures stretch light years across the nebula, their perfectly aligned shapes betraying the hand of some hidden force. Unlike the chaotic filaments visible in X-rays or optical light, these radio-only jets maintain astonishing symmetry, as if sculpted by an invisible chisel. Their crisp boundaries and directional precision suggest something extraordinary: a secret magnetic scaffold, a framework too faint to see directly but powerful enough to keep these streams perfectly on course. What makes these jets so puzzling is their selective visibility. While Hubble and Chandra see only tangled gas where the jets should be, radio telescopes like the Very Large Array reveal them in stark clarity, pulsing with synchrotron radiation, the telltale glow of electrons spiraling along magnetic lines. This wavelength-dependent invisibility hints at a unique particle population within the jets: ultra-high-energy electrons that emit predominantly in radio frequencies, either by design or because some filtering mechanism strips away their ability to radiate at higher energies. Imagine a highway where only certain cars have headlights. That's essentially what we're seeing here, a cosmic thoroughfare visible only through its radio glow. The structure of these jets defies conventional jet physics. Typically, astrophysical jets, like those from quasars or young stars, taper smoothly as they expand. But the Crab's radio jets maintain near-constant width over vast distances, resisting the dissipative forces that should fray their edges. One theory proposes they're encased in cylindrical magnetic sheaths, helical fields that act like self-reinforcing tunnels, preventing particle escape. Supporting this, polarization maps show the jet's magnetic fields twist along their lengths like the grooves of a rifle barrel, possibly keeping particles focused through a phenomenon called the hose instability, where magnetic tension counters outward pressure. Then there's the mystery of their intermittent nature. Unlike the nebula's persistent X-ray jets, these radio structures flicker in and out of detectability over months. Some sections appear hollowed out for years, then suddenly refill with radiating particles, as if some cosmic valve periodically opens and closes. The leading explanation involves magnetic reconnection events far from the pulsar, explosive rearrangements of field lines that sporadically inject fresh electrons into the jet channels. But why these injections would favor radio-emitting particles over others remains unexplained. Most intriguing are the jet's knots, bright beads spaced at regular intervals like pearls on a necklace. These might trace standing shock waves where the jet rams into slower-moving nebula gas, compressing particles into glowing clumps. Alternatively, they could mark resonance points where the pulsar's spin frequency harmonizes with the jet's oscillation modes, creating zones of constructive interference. Either way, their precise spacing suggests an underlying mathematical order to what otherwise seems like pure chaos. The invisible architecture guiding these jets may hold the key to one of the Crab's grander mysteries, how it redistributes energy across such vast scales. These radio-only structures could be the hidden plumbing of the nebula conduits ferrying energy and particles from the pulsar to its outermost reaches without the usual radiative fanfare. If so, they're challenging our very definition of what a jet can be, proving that sometimes the universe's most important structures are the ones we can barely see. Lashing through the Crab Nebula's luminous chaos like a cosmic scar, an uncanny streak known as the dark lane defies easy explanation. This persistent shadow, spanning nearly half a light-year, isn't just an absence of light, it's an active obstruction, bending radiation around it like a celestial stealth cloak. While most nebula features glow or shimmer, this one stubbornly swallows light across multiple wavelengths, from visible to infrared, leaving astronomers to wonder, what kind of structure could cast such a profound shadow in a vacuum supposedly filled with tenuous gas? Clues emerge from the lane's razor-sharp edges. Unlike typical dust clouds which fray like cotton candy in stellar winds, this formation maintains knife-edge boundaries that refuse to dissipate. Submillimeter observations reveal it's packed with super dust grains of carbon and silicate up to 10 times larger than average interstellar particles, clumped together with bizarre cohesion. Normally, radiation pressure should blast such dust apart, yet here it clings like iron filings to a magnet. One theory suggests electrostatic forces are at play, with individual grains acquiring opposite charges that lock them into a rigid, lattice-like structure. Laboratory experiments with plasma crystals show similar self-organizing behavior, but never before observed on interstellar scales. Then there's the lane's uncanny motion. Over 2 decades of Hubble observations show it drifting sideways at a steady 1,500 kilometers per second, far too slow to be a pulsar jet, yet too fast for ordinary nebula debris. This Goldilocks velocity points to a possible origin, a chunk of the progenitor star's carbon-rich outer layers flung outward during the supernova but not fully vaporized. Spectroscopy detects enhanced levels of heavy elements like strontium and zirconium along the lane's length, supporting the idea of stellar shrapnel. Yet this doesn't explain its shadow-casting power. Even dense stellar material shouldn't block X-rays as effectively as this structure does, unless it's somehow magnifying its opacity through quantum-scale tricks. The darkest mystery lies in what the lane reveals when backlit by the pulsar's gamma rays. Instead of a uniform shadow, high-resolution scans show intricate substructures thread like tendrils and knotty protrusions that resemble the fractal branching of a lightning bolt. These features pulse faintly in sync with the pulsar's rotation, suggesting the lane isn't just passive debris but an active participant in the nebula's energy dynamics. Some researchers speculate it could be a cosmic-scale Lichtenberg figure, the scarring left when an intense electromagnetic discharge etches itself into material. If true, the lane might be a fossilized snapshot of the supernova's first millisecond, when unimaginable currents surged through the dying star's corpse. Perhaps most unsettling is the lane's gravitational footprint. Precise tracking of nearby filaments reveals subtle warping, as if an unseen mass lurks within the darkness. Estimates suggest something equivalent to 20 Earth masses hides there, too diffused to be a black hole, yet too hefty for a mere dust cloud. This has revived speculation about quark nuggets, hypothetical ultra-dense remnants of the early universe that could have seeded the original star's collapse. While purely theoretical, such objects would explain both the lane's heft and its weird ability to dampen radiation across the spectrum. The dark lane refuses to fit neatly into any cosmic category. It's not quite a dust lane, not quite a shadow, not quite a debris field, but something in between, a hybrid phenomenon that challenges how we define structures in space. And with every new observation, it taunts us with the same unanswerable question. In a nebula where even the darkness shines with secrets, what other unseen architects are shaping the Crab's chaotic beauty? Even amid the Crab Nebula's relentless fireworks, few phenomena are as hypnotic or as baffling as its flickering ultraviolet lights. Unlike the predictable pulses from its neutron star heart, these UV fluctuations dance to their own erratic rhythm, brightening and dimming like candle flames caught in an unseen cosmic breeze. Some regions flicker rapidly, their UV output changing by up to 30% in mere hours, while others ebb and flow over weeks with no discernible pattern. The strangest part, these variations don't align with the pulsar's spin or its gamma-ray outbursts, as if the nebula has developed a secret second heartbeat. At first glance, the culprit seems obvious: synchrotron radiation, the same process lighting up the rest of the nebula, where electrons spiral around magnetic fields and emit light. But synchrotron emissions should be relatively stable, their brightness tied to the pulsar's steady particle wind. Instead, the UV hotspots behave more like living organisms flaring unpredictably, sometimes even passing their flickers to neighboring regions like a game of cosmic telephone. Hubble's ultraviolet sensors have captured these contagious brightness waves rippling through filaments, with delays suggesting propagation speeds far slower than light or shock waves. It's as if the nebula is transmitting signals through some hidden medium we can't yet detect. One leading theory involves magnetic mirrors, transient structures where field lines bend into parabolic shapes, trapping UV-emitting electrons like fireflies in a jar. When these mirrors destabilize, they could release accumulated particles in sudden bursts, creating the flickering effect. Supporting this, some UV flares correlate with subtle X-ray shifts, hinting at underlying magnetic rearrangements. Yet other flares occur in isolation, their triggers buried too deep in the nebula's chaos for current telescopes to resolve. Then there's the enigma of the UV deserts, pockets where ultraviolet light should thrive given the local particle density but remains eerily absent. These zones seem to act like sponges, absorbing or scattering UV photons without re-emitting them. Spectroscopic clues point to unusual dust compositions, possibly metallic nanoparticles that convert UV energy into invisible infrared vibrations. If confirmed, it would mean the nebula isn't just generating mysterious UV flickers, it's also hiding them in plain sight. The most tantalizing flickers come from the nebula's outer fringes, where UV light pulses with near-clockwork precision every 43 days. Unlike the central chaos, these oscillations are remarkably clean, resembling the heartbeat of a hidden celestial metronome. Some researchers suspect a debris disk orbiting an unseen companion star, its periodic eclipses dimming the UV glow. Others propose a more exotic explanation: magnetospheric echoes, where the pulsar's magnetic field lines vibrate at resonant frequencies, strumming the nebula's plasma like guitar strings tuned to ultraviolet notes. Every unexplained flicker forces us to confront how little we grasp about energy's journey through space. The Crab Nebula isn't just a static light source, it's a dynamic UV theater, with curtains that rise and fall on stages we're only beginning to map. And with each enigmatic pulse, it reminds us that even the highest energy light can carry whispers of mysteries darker than the void itself. Among the Crab Nebula's most bewildering sights are slender filaments that stretch across the void like cosmic marionette strings, delicate, luminous threads that appear to connect regions separated by light years. At first glance, they resemble ordinary nebula structures, but a closer look reveals something far stranger. these filaments don't just drift randomly, they align with eerie precision, forming geometric patterns that hint at an invisible scaffolding. Some even pulse in unison, as if tugged by forces beyond the reach of conventional physics, sparking whispers among theorists that we might be glimpsing the fabric of spacetime itself. The most striking example is a filament dubbed Ariadne's thread, a near-perfect straight line of ionized gas linking the pulsar to a distant knot of energized particles. Normally, such structures would curve or fray under the nebula's chaotic magnetic storms, yet this one remains rigid, defying the turbulence around it. Spectroscopic analysis reveals its particles are vibrating in sync, a coherence typically seen only in engineered systems like fiber optic cables, not the wilds of interstellar space. One radical interpretation suggests the filament could be a cosmic scale, string, formed by quantum vacuum fluctuations, a temporary knot in spacetime's fabric where energy flows unnaturally smoothly. It's a concept borrowed from theoretical physics, where similar structures might form in the extreme conditions following a supernova, acting as conduits for energy transfer that bypass ordinary electromagnetic rules. Equally puzzling are the bridge filaments, tenuous strands that arc between seemingly unrelated regions of the nebula. When mapped in 3D, some trace out perfect parabolic curves as if anchored by unseen masses. Yet no detectable gravitational source explains their paths. This has led to speculative but thrilling ideas. Could these be relics of quantum entanglement left over from the star's collapse, where particles separated by vast distances still influence one another? Or perhaps evidence of higher dimensional geometry, where the filaments are projections of structures we can't fully perceive, like shadows of a fourth-dimensional web? The debate intensifies when examining the filament's light. Some emit polarized radiation at angles that shouldn't be possible given the nebula's magnetic field orientation, implying an additional, hidden force is at work. Others flicker in patterns resembling standing waves, the kind you'd see in a vibrating violin string, suggesting they're under tension from something we can't measure. If confirmed, this tension might hint at exotic physics, where spacetime itself acts like an elastic medium, resisting distortion in ways predicted by string theory but never before observed in nature. Skeptics argue these are just chance alignments, mundane structures viewed from angles that create illusions of connection. But the statistical unlikelihood of so many perfect alignments in one nebula keeps the mystery alive. Every new observation adds layers to the puzzle, from filaments that abruptly change direction at mathematically precise angles to ones that vanish when observed at certain wavelengths, as if cloaked by some quantum trick of the light. Whether cosmic strings or celestial mirages, these filaments challenge our assumptions about how matter organizes itself in the universe's most extreme environments. They might be signposts to new physics or simply reminders of how nature's artistry can outpace our imagination. But one thing's certain, in the Crab Nebula, even the seemingly simple threads of gas come with knots we've yet to untangle. The Crab Nebula's shockwaves should fade with time, dissipating like echoes in a canyon as they expend their energy. Yet some persist for centuries, defying the laws of entropy with the stubbornness of a cosmic heartbeat that refuses to slow. These eternal shock fronts carve through the nebula's guts, not just surviving but thriving, maintaining razor-sharp edges and velocities that mock our best simulations. It's as if the nebula has hidden power outlets, secretly recharging shockwaves that should have fizzled out generations ago. Take the most infamous example, the Rim of Doom, a crescent-shaped shock nearly a light year across that's been visible since the nebula's discovery. Based on its expansion speed and energy output, it should have dissolved into gentle turbulence by the 19th century. Yet today, it's as vibrant as ever, glowing fiercely in X-rays and even accelerating in some sections. High-resolution spectra reveal the shock's secret layers of particles stacked like a cosmic onion, each shell moving at slightly different velocities. This isn't a single dying wave, it's a nested set of shocks with fresh energy injected from behind like a conveyor belt of violence. The question is, what's powering this conveyor belt? The pulsar's wind can't explain it. The rim lies too far askew from the neutron star's jets. One theory points to rogue magnetic vortices, whirlpools of energy that form when field lines tangle too tightly. These vortices might act like natural particle accelerators, funneling energy into the shock's backside fast enough to offset its decay. Imagine a wildfire where new sparks constantly leap ahead of the flames, igniting fresh fuel before the main blaze can die. That's the kind of self-sustaining chaos we might be witnessing. Even stranger are the standing shocks, structures that don't propagate outward but vibrate in place like plucked guitar strings. The James Webb Space Telescope recently spotted one near the nebula's core, flickering at a steady 43 Hz frequency. At this spot, gas moving inward at half the speed of light collides with an invisible barrier, creating a stationary shock that hums for months before vanishing. Some researchers suggest these could be resonance zones, where the pulsar's spin frequency matches natural oscillation modes in the nebula's plasma. Others speculate they're evidence of magnetic mirrors, regions where field lines bend so sharply they act like rubber sheets, reflecting particles back into the fray. The grandest mystery lies in the shockwave's longevity. Shock physics dictates they should lose energy to radiation, particle acceleration, and heat. Yet Chandra's observations show some crab shocks radiating less energy than they're theoretically expending, a thermodynamic violation akin to a light bulb glowing brighter while using fewer watts. The only explanation, an invisible energy source, something our instruments can't yet detect. Dark matter annihilation has been floated as a wildcard possibility, where hypothetical particles collide and decay within the shocks, providing clandestine fuel. Less exotic but equally puzzling is the idea of cosmic recycling, where the shocks themselves harvest energy from the nebula's turbulent magnetic fields, becoming self-sustaining entities. Every undying shockwave in the Crab Nebula forces a humbling admission. Our understanding of cosmic violence is incomplete. These aren't just remnants of a star's death throes, they're living, evolving structures that cheat time and physics with gleeful abandon. And with every new observation, they challenge us to rethink one of astrophysics' oldest questions. In a universe ruled by entropy, how does anything manage to stay so fiercely, brilliantly alive? Among the Crab Nebula's countless enigmas, one of the most visually arresting is its eerie symmetry, not just in its glowing filaments or magnetic fields, but in something far more fundamental, the very elements that compose it. When astronomers map the distribution of heavy metals like iron, nickel, and titanium across the nebula, they don't find the chaotic scatter expected from a violent supernova. Instead, these elements arrange themselves in near-perfect mirrored patterns, as if the explosion's debris field were reflected across an invisible axis. It's like watching an inkblot form in zero gravity, where every splash on one side finds its twin on the other, a level of order that defies the randomness of stellar death. This mirroring first caught scientists' attention when spectral imaging revealed elemental twins, pairs of gas clouds with nearly identical compositions, positioned like bookends around the pulsar. One cloud, rich in strontium and barium, would have a counterpart on the opposite side with the same unusual mix, even though the two regions showed no direct physical connection. In most supernova remnants, heavy elements are strewn haphazardly, their distribution shaped by turbulent mixing and asymmetric shocks. But the Crab's symmetry suggests something extraordinary. The original explosion might have been far more orderly than anyone imagined, or some unseen force has been meticulously sorting the wreckage ever since. One compelling theory points to the progenitor star's magnetic field. If the dying star's core was threaded with an exceptionally strong, organized magnetic field at the moment of collapse, it could have funneled the supernova's ejector into twin outflows like water forced through symmetrical nozzles. Supporting this, some simulations show how a dipole magnetic field, think of a bar magnet's orderly lines, can sculpt exploding stellar material into mirrored lobes. Yet even these models struggle to replicate the Crab's precision, particularly in elements like iron, which should have been flung far more chaotically from the star's turbulent core. Then there's the wild card role of the pulsar's current magnetic influence. Over centuries, its relentless particle wind might have acted like a cosmic comb, rearranging stray atoms into coherent patterns. Imagine blowing smoke rings into a fan. Initially random puffs could organize into repeating shapes under the right conditions. In the Crab's case, heavy elements, being more resistant to radiation pressure, could have been piled into symmetrical zones while lighter gases were swept away. Spectroscopic evidence hints at this. Certain metal-rich filaments show layered structures akin to tree rings, suggesting gradual accumulation under a steady directional force. The most tantalizing symmetry lies in the nebula's ion distribution. Iron 56, a hallmark of supernova nucleosynthesis, typically forms deep in a star's core and gets blasted outward unevenly. Yet in the Crab, iron isn't just evenly distributed, it's arranged in concentric shells, like the layers of an onion, with each shell's thickness and spacing repeating on either side of the pulsar. This level of organization implies a previously unknown feedback mechanism, where the nebula's magnetic fields and shockwaves somehow remember and replicate spatial patterns across vast distances. What makes this mirroring so revolutionary isn't just its beauty, it's the implications for how elements spread through the cosmos. If supernova can produce such orderly debris fields, our assumptions about how galaxies are seeded with heavy metals might need rewiring. The Crab Nebula, ever the iconoclast, seems to be showing us that even in the most violent cosmic events, there's a hidden geometry, a silent, elegant order waiting to be decoded. And every symmetrical element pair whispers the same haunting question. In a universe ruled by chaos, who or what is holding the mirror? The Crab Pulsar should be the universe's most reliable timekeeper, spinning with metronomic precision, its lighthouse beam sweeping past Earth 30 times every second like the world's most accurate cosmic clock. But this neutron star has other ideas. Without warning, its spin stutters, speeds up, or slams on the brakes in events astronomers call glitches, sudden changes in rotation rate that defy every model of stellar behavior. These aren't tiny hiccups. In milliseconds, the pulsar can gain or lose a millionth of its rotational speed, equivalent to a figure skater abruptly changing spins mid-twirl with no push or pull. What makes these glitches truly bizarre isn't their existence. Other pulsars glitch occasionally, but their sheer unpredictability. Most pulsar irregularities follow rough schedules, like Old Faithful's eruptions or a car needing maintenance after so many miles. The Crab Pulsar laughs at such patterns. It might glitch twice in a month, then go silent for years. The events vary wildly in strength too, from barely detectable tremors to violent jerks that release more energy than a solar flare. During one extreme glitch in 1989, the pulsar suddenly spun 1 part in a billion faster, enough to make its magnetic field briefly outshine the entire nebula in gamma rays. The leading explanation points to the pulsar's exotic interior. Beneath its solid crust lies a superfluid ocean, neutrons flowing without friction, behaving more like liquid helium than normal matter. When this superfluid's vortices suddenly unlock from the crust, they could transfer angular momentum in bursts, like a spinning ice skater pulling their arms in. But here's the problem. Models predict these events should cause slowdowns, not speed-ups. The Crab's glitches often do the opposite, spinning faster as if kicked by an invisible hand. Then there's the mystery of the anti-glitches, rare events where the pulsar slows abruptly. In 2011, it lost a staggering 10 nanoseconds from its rotation period in just 6 hours. No known process in neutron star physics accounts for this. Some theorists speculate it might involve crustal starquakes, where the neutron star's surface fractures under intense magnetic stress, momentarily increasing its moment of inertia. Others propose chunks of the superfluid core momentarily crystallizing, like water freezing into ice, stealing rotational energy in the process. The most perplexing glitches show no energy release at all. The pulsar's spin changes without the expected X-ray or radio bursts. It's as if something inside is silently rearranging itself, invisible to our telescopes. Recent gravitational wave detectors have been trained on the Crab during glitches, searching for ripples in spacetime that might betray internal collapses or phase transitions. So far, nothing, just more questions. Perhaps the most revolutionary idea comes from quantum physics. The pulsar's core might harbor strange matter, a hypothetical state where neutrons dissolve into free quarks. If pockets of this quark gluon plasma form and decay unpredictably, their changing density could alter the star's rotation like passengers shifting in a spinning carnival ride. Supporting this, some glitches correlate with changes in the pulsar's gamma-ray emission profile, hinting at deep structural shifts. Every unannounced glitch forces astronomers to reconsider what neutron stars are truly made of. The Crab Pulsar isn't just challenging our models, it's revealing gaps in our understanding of matter itself. And with each unpredictable lurch, it reminds us that even the densest objects in the universe can still surprise us. Just when you thought the Crab Nebula had shown all its cards, infrared telescopes reveal yet another layer of mystery, ghostly rings rippling outward from the wreckage like whispers from the star's final days. These aren't the sharp, glowing hoops you'd expect from shockwaves or pulsar winds. They're spectral imprints, barely visible even to the most sensitive instruments, tracing faint concentric circles around the nebula's core in wavelengths invisible to human eyes. The James Webb Space Telescope captured them in startling detail, delicate halos of dust, each separated by light years, pulsing with the quiet rhythm of a cosmic countdown. What makes these rings extraordinary isn't just their subtle beauty, it's their improbable survival. Supernova are the universe's ultimate wrecking balls, blasting apart stellar surroundings with enough force to erase any pre-existing structures. Yet here they are, these orderly loops, preserved like tree rings in a celestial fossil. Their composition holds the first clue: silica and graphite dust, materials typically shed by aging stars in their final millennia. This suggests the rings are relics of the progenitor star's death throes, ejected in a series of pre-supernova outbursts anywhere from 10,000 to just a few hundred years before the final explosion. Imagine a dying star coughing smoke rings into space, each one a timestamp of its escalating instability. The real puzzle lies in their perfect spacing. Unlike chaotic debris fields, these rings are mathematically precise, their intervals corresponding to periods of roughly 50 to 100 years. That regularity points to a rhythmic mass loss process, possibly tied to the star's pulsations as it teetered on the edge of collapse. One theory suggests helium's shell flashes violent thermal convulsions in the star's core could have triggered these periodic ejections like a cosmic geyser on a strict timetable. Supporting this, chemical signatures in the outermost rings show enhanced carbon and oxygen, the telltale ashes of helium burning. But here's where it gets weird. Some rings aren't just passively drifting, they're expanding faster than the nebula's known shockwaves, as if propelled by an unseen force. The innermost ring, for instance, races outward at nearly 2,000 kilometers per second, far exceeding the pulsar wind's measured push. This has led to wilder speculation. Could magnetic fields frozen into the dust be interacting with the nebula's own, creating a particle-accelerating feedback loop? Or perhaps the rings are surfing on gravitational waves left over from the supernova itself. They're lightweight dust grains responding to ripples in space-time that heavier materials ignore. Then there's the enigma of the missing rings. Infrared surveys reveal gaps in the sequence intervals where concentricity breaks down entirely. These might be scars from earlier, weaker eruptions that dissipated over millennia, or evidence of a companion star's gravitational tug warping the dying star's ejector. The most tantalizing void sits just half a light-year from the pulsar, a suspiciously clean circle devoid of dust. Some researchers wonder if this marks where a planet, or even a brown dwarf, was vaporized in the supernova's blast, its ashes swept away too quickly to form a lasting ring. These phantom circles aren't just celestial curiosities, they're time capsules preserving the progenitor star's final acts with forensic precision. Every grain of dust in those rings carries isotopic signatures that could reveal the star's mass, composition, and even the precise trigger for its demise. And as infrared telescopes grow more advanced, these faint halos may yet unveil their full story, a secret history written in dust waiting patiently in the dark to be read. Even in its grand, slow-motion ballet of expansion, the Crab Nebula refuses to follow the script. Most supernova remnants swell outward at a steady pace, their edges advancing like a predictable tide. The crab, however, breathes, its gaseous tendrils sometimes surging forward with unexpected vigor before mysteriously slowing, as if the entire nebula is inhaling and exhaling against some cosmic rhythm. Hubble's time-lapse observations reveal this odd cadence. Over 20 years, certain filaments raced outward at 1,500 kilometers per second, only to stall abruptly for years before lurching forward again. Others moved in fits and starts like a car with a sticky accelerator, leaving astronomers to wonder what invisible hand is pressing and releasing the nebula's gas pedal. The leading suspect, the pulsar's magnetic fist. Normally, a neutron star's relentless particle wind pushes debris outward uniformly, but the Crab Pulsar's magnetic field is so knotted, so violently dynamic, that it might be squeezing the nebula in an intermittent cosmic grip. Imagine trying to blow up a balloon while someone randomly pinches different spots. The air wouldn't escape smoothly. Similarly, when magnetic reconnection events snap in the nebula's depths, they could create temporary pressure valves, regions where energy bursts accelerate nearby gas while leaving other zones untouched. Supporting this, X-ray maps show expansion surges often coincide with gamma-ray flares, suggesting a direct link between the pulsar's tantrums and the nebula's uneven growth. Then there's the shockwave paradox. In some regions, the nebula's outer shock front actually retreats, a phenomenon never observed in other supernova remnants. It's as if those areas are being sucked backward, defying the laws of momentum. One explanation points to denser interstellar material lurking beyond the visible nebula, creating pockets of resistance where shocks rebound like ocean waves hitting a seawall. Yet spectroscopy reveals no such dense barriers. Instead, researchers speculate the retreat might trace back to the original supernova's asymmetry. If the explosion blasted more material in one direction, recoil forces could still be tugging parts of the nebula inward like a stretched spring snapping back. The most baffling behavior appears in the nebula's whispering zones of filaments that expand and contract rhythmically every few decades. These aren't random jitters, they're precise oscillations, as if the gas is tethered to some unseen anchor. One theory suggests these filaments might be caught in magnetic resonance, vibrating like guitar strings plucked by the pulsar's spin. Others propose they're surfing on gravitational waves from the original supernova, ripples in spacetime that periodically stretch and compress the nebula's fabric. If true, it would mean the crab isn't just expanding, it's humming along to the aftershocks of its own birth, a cosmic melody written in motions too subtle for human eyes to see. What makes this breathing motion revolutionary isn't just its defiance of expectations. It reveals the Crab Nebula as a living system where energy doesn't just dissipate, it circulates, resonates, and occasionally rebels. Every inexplicable surge, every mysterious pause, is a reminder that even in death, stars can harbor rhythms we're only beginning to sense. And as long as the crab keeps breathing, we'll keep watching, waiting to decode the secrets of its celestial lungs. From its runaway pulsar to its whispering radio waves, its phantom filaments to its cosmic cold spots, the Crab Nebula isn't just a stellar graveyard. It's a relentless rebel, rewriting the rules of astrophysics one anomaly at a time. Every flicker of light, every rogue particle, every inexplicable shadow forces us to confront how much we still don't understand about the universe's most extreme environments. Think about it, we're observing a structure just 6 light-years wide that somehow produces gamma-ray flares hotter than galaxy clusters, accelerates particles faster than our most powerful colliders, and sustains magnetic storms so chaotic they'd shred planets in seconds. This nebula's 30 strangest phenomena aren't just cosmic quirks, they're clues. The way its filaments move like living tendrils challenges our models of fluid dynamics in a vacuum. Its antimatter surplus hints at undiscovered particle physics. Those frozen dust grains, they might be teaching us new quantum tricks. Even the nebula's breathing expansion suggests that supernova remnants aren't static relics but dynamic ecosystems, pulsing with hidden energy flows we're only beginning to trace. What does it all mean? That the universe is far weirder, far more inventive than our textbooks dare to suggest. If a single stellar corpse can defy this many expectations, imagine what other cosmic rule-breakers lurk in the dark, waiting to be found. Maybe there are nebulae where gravity flows backward, or pulsars that spin faster than physics allows, or phenomena so bizarre we lack the language to describe them. The Crab Nebula is proof that discovery didn't end with Hubble or Einstein. It's happening right now, in real time, in the data streams of telescopes trained on this tangled knot of gas and light. So here's the real question: which of these 30 phenomena left you utterly stunned? Was it the gamma-ray flares that outshine galaxies, the bullets of matter punching through space at near light speed, or maybe those ghostly light echoes replaying a star's death across centuries? Drop your pick in the comments, and while you're at it, take a moment tonight to glance toward Taurus, where this cosmic enigma spins its riddles into the void. After all, the next great mystery might already be flickering into view, just waiting for someone like you to notice.